And welcome back to another exciting video hosted by Turdferg67, your link for top quality physics education and really bad jokes. Okay, so anyway, this video is, again, as the title says, rotational motion review is what we're looking at. So essentially what we're talking about are objects that are traveling in circles. And this is a review. Hopefully you've already kind of studied this out a little bit, but we're still going to go into it a little bit. So the fundamental things in terms of us going in a circle, things that you'll have to be able to do. This video is just going to be a review of equations. So first off, we've actually got this angle. And now what's funny, we're used to calling this an angle, but in terms of now, theta, we're actually going to call that an angular displacement. An angular displacement is actually what it is. Because just like you can go off and you start walking through the woods and you'll see a problem where it says, hey, somebody walks through the woods, da, 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 da. And it might say they walk 20 meters. Maybe they have really shortness of breath. But anyway, they walk 20 meters and we'd say, well, this person has an X, a displacement maybe of 20 meters as they walk through the woods. Well, in this problem, you might have a person on the outside of a merry-go-round. And now it might say that the person, let's say that the person rotates 2 revolutions is what it says. So this person rotates 2 times around the merry-go-round. So they go 2 times spinning around the merry-go-round. What is that trying to tell us? It's trying to tell us that they have an angular displacement of 2 revolutions. And you're like, Mr. Cole, I got this. This is easy. Well, there's just one thing to keep in mind, and that's that none of the problems in this chapter will work with revolutions. We have to have all our angles, our angular displacement, in the units of radians that we actually have to use, which you've learned in your math class before. 1 revolution is equal to what? 2 pi radians. So in the case of this problem, what would be our theta for somebody going 2 complete laps on maybe a merry-go-round? Well, they would have 4 pi radians would be their displacement in this case. Or you might even go and say 12.56 radians if you did not want to include pi in your answer. And by the way, in most physics classes, pi is not. Now, if you're taking like a free response question or something like that, they should not object to your use of pi. So anyway, we're familiar now with what this theta actually represents in these problems. And it may not be a person on a merry-go-round. It could be the merry-go-round itself. You would still identify like a point on the rim of the merry-go-round and then picture if it rotated 2 revolutions. Vice versa, you might have a cylinder on a hill. So you might have a cylinder. It's a classic physics problem. I've worked examples like those elsewhere on my channels. As this object rotates, it's the same thing. You might have to identify and say that, let's just say it makes 1 revolution. Then your displacement angularly was a 2 pi radian displacement as it rolled down the plane if it rolled 1 time. Now, the other things you're going to need in order to work this problem, you need to be able to identify that that is your radius. And then the other thing that's a little odd, that's this piece of the circumference. We know that if you go all the way around distance-wise a circle, that's what's called as circumference. But what we routinely talk about is what we call an S. And that S is called an arc length. And we call that arc length. And so in terms of what arc length is, what's cool is if you would go back down and take a look to the object rolling down the hill. So as it rolls down the hill, we have an X displacement. Well, the cool thing is that X displacement is the same thing as this arc length. They're equal to each other. So the distance around the outside of the circle would match the displacement that the object occurs while rolling down the hill. Now, very common, your first introductory equation in the things moving in circles is that theta is equal to S over R. It's equal to, remember, all pi is, it's a ratio of the distance around the outside of the circle to your arc length, and that's where we get our 3.14 from. But anyway, so as we take a look and kind of fill this out a little bit more, we also, this is not an equation, but look at what you can also do. You can also kind of cheat and say that, check that out, that theta then is also equal to x over r. So this arc length and this position, they're the same thing. We can interchange in most of the problems. So kind of keep that in mind. Again, your radius is quite simply your radius. So let's see if we can scroll down, kind of continue doing this video a little bit more. So our first introductory equation is that. All right, so let's do this. Go back to linear problems. When you're doing a linear problem, we usually start out with saying that like velocity is equal to a change in distance over a change in time. Well, what's cool is in rotational motion problems, we have the same thing. So check this out, delta theta over delta t. We've got the same thing going on. So we've got equivalent equations, whereas this one we just call velocity. When an object is rotating or moving in a circle, we call this one angular velocity. And whereas this guy over here is in meters per second, well, remember, what is it we said we have to measure our angles in, our angular displacements? In radians, so that means that angular velocity, and by the way, that is not the letter W, it's actually a lowercase Greek omega. If you remember capital omega, and that's the worst capital omega I've ever drawn. I'd like to apologize to all the Greek people in the world for my destruction of that. Ugly. Okay, it's not getting any better. But anyway, now that we've had our Greek alphabet primer, know that this omega is then measured in radians or rads per second. So there's kind of our introductory equation. Likewise, the basic equation for linear acceleration is what? A change in velocity over a change in time. Well, likewise, we have what's known as angular accelerations. And in the event of angular accelerations, we know what? That would be a change in angular velocity over a change in time. And so we know that linear acceleration is measured in meters per second square. Angular acceleration is then measured in radians per second square. All right, now let's do this. What about in terms of kinematics? So kinematics, we know we've got equations like this, V sub O plus AT. For those of you that like to use VF and VI, sorry, I'm not. I just can't make that conformity in my life at this time. Well, just like this is a linear kinematic equation for velocity and acceleration, we've got the same kinematic that exists in rotational motion, or as I like to say, in circle world. So we've got the same thing. Here's our final angular velocity. Here is our initial angular velocity. There's our acceleration. There's our time. Other equations. We know that theta is equal to, well, I'm completely jacking it. I forgot. This is linear problems. We know that x, or delta x, is equal to VOT plus 1/2 AT squared. Well, what's cool is over on the other side, we know then that theta, the equivalent of x, is equal to omega OT plus 1/2 alpha t squared. And then let's kind of keep on going. And what about our timeless equation? Velocity square is equal to VO squared plus 2 alpha theta. Wow, did anybody just catch how I totally wrecked that? My brain is so engaged in the circle world that I forgot that when we're talking about these problems is just 2ax. So there's our timeless kinematic equation for a linear world. And so we know that over here, angular velocity square would be equal to omega O square. I once had a student said he planned on inventing a cereal called Omega O's. He actually now makes a lot of money working for Intel. Steven, shout out. When are you going to make my Omega O's cereal? Anyway, moving on to alpha theta. And so there's our equivalent. By the way, people always also kind of forget this. Go back to the very beginning. I should do something to this first equation. We usually say that that is an average velocity, and so likewise, we should also do that over here. Average angular acceleration. This is typically an average acceleration. Average. I know that's just a formality, but I kind of like, well, being formal. So that's okay for me to do that kind of stuff. But here's one people always forget, and it comes in handy. Another, as I make a random scribble, because my little pad is acting weird. Another thing to remember is this, velocity average. This is what made me think about that. Remember, all you have to do, if you know your initial and final velocities, you can find your average velocity just by doing this. And that's very handy. And likewise, the same thing's true for objects that are in rotation. If you need to find an average angular velocity and you have 2 velocity, then we can use this equation as well. So anyway, this is our intro. Now, what's cool is this. You should notice how these two worlds kind of have all this in common with each other. They look the same. And likewise, we can write 3 equations that let us combine these two worlds. Because the thing is that you've got to always be in consideration is this. Say, for example, you've got an object like a car tire rolling on the ground. So here's my car tire. Get some lug nuts on there. And this tire is rolling. Well, as the tire is rolling. Sorry, nobody will probably get that joke. But as this tire is rolling along the ground and it's making a horizontal displacement, the thing is you've got to also think about is the fact that it also has this arc length. And this arc length is the same as this x. So if you remember at the beginning, we talked about the basic equation for arc length is S over R, Rx over R. So there's 3 equations I want you to have, and we could derive those. But I know that theta is equal to S over R, and you should be saying, Mr. Cole, why don't you just write X? Well, I know it's the same, but I can't bring myself because it's not always going to be true that that's X over R. But still, it's very handy to have this equation because if we have theta and a radius, then we can actually figure out how far something rolled by using this equation. Here's another equation. Linear velocity is equal to r omega. So say, for example, you're working a problem and it gives you the initial velocity of the car. So let's say it gave you this v sub 0 over here. Well, if it gives you that v sub 0 and it gives you a radius, then that means you can also find your omega O initial as well. And then likewise, we know that linear acceleration is equal to r alpha. Now, the only thing you may see different in some textbooks is they will put like a little t beside these and refer to those as tangential velocity and tangential acceleration, which I'm using the term linear, which of course is effectively the same thing. So I don't usually write the little t's in there. But anyway, so the next video in this series will actually work a couple of problems using all these equations. So until next time, be cool, stay safe. Later, dudes.